Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of From Scratch, it's the start of a new series where we're going to be building programs from scratch. So in our other series, we mainly look at code that I've already written and then go over the details briefly and kind of the high-level concepts. In this one, we're going to kind of dig in the weeds a lot more and show if you were to write this code yourself, how would somebody else, or how would you go about writing it? So we'll start out with the GPU program today. Right, so this was from our CUda Crash Course series, and it's just vector addition. Right, so we'll go ahead and open our application. Right, so vector add.cu, that's what we'll be writing. And we can just say that this program computes the sum of two arrays on the GPU using CUda. Right, and then who's the program by, right? And it'll be by me, Nick, from Coffee Before Arch. Okay, so I generally start out by doing some boilerplate code, right? So we need a main function, and we'll need a kernel, right? We'll need our vector add kernel. So kernels, you'll generally use this __ global __, and this just says that it's a device function, or it's a function that will, it's a kernel that will be called from the host and run on the device, right? So called from the CPU, runs on the GPU. If you have __ device __, that's a function that's called from the GPU and runs on the GPU. And then you can even have host as well, which is just the opposite, right? It just runs on the CPU. Or it's called from the CPU, runs on the CPU. Okay, right, so we can have, this will be a void function, right? These functions don't return anything from the GPU. Right, and there's our vector add kernel, right? And we can just say computes the sum of two arrays. Okay, so the first thing that I generally do, right, especially for simple code like this, is you set up your problem, your input information first, right? So we can say set our problem size, and then we can give it a default, right? Default equals 2 to the 20. And then I usually just use in as the number of elements, right? So int in equals 1 shifted over 20 times. That's the equivalent of 2 to the 20. And then we generally calculate the number of bytes it takes to store 2 to the 20, right? So we'll do vector addition for integers. So bytes in this case will just be equal to in times size of bytes, right? And so this is nice because now when I'm doing if I need to change my problem size, I can go ahead and just change one thing, right? And I don't have to change anything dealing with allocation later, because the allocation information, or how many bytes we need to allocate, is just based upon the number of elements, right? So this makes your code pretty concise later on. Okay, so the next thing we can do is we'll go ahead and set up our pointers, right? So, or we'll go ahead and allocate some memory for inputs, outputs, right? So here we'll have 3 pointers, right? So we'll have int pointer A, pointer B, and then pointer C, right? So this, it will have array A plus array B is equal to array C. And then in this case, right, we'll go ahead and use CUda, unified memory, right? So this is a really, convenient thing, especially if we, we're looking for readability and usability of our code. Because now we don't need to worry about directly doing mem copies to the GPU or from the GPU. That just the memory automatically gets paged to and from the device, right? So we'll go ahead and just allocate some space here using CUda malloc managed, right? So if we use CUda malloc managed, we can access it on both the host and the device. If we use CUda malloc, we can only access it on that memory is only on the GPU. So here, we'll just allocate some space for A, so we pass in the address of A and then the amount of memory, right? So we calculate that ahead of time, that's bytes, right? And then it'll be the exact same amount of memory for all 3 of these, right? So for both A, B, and C, right? Because an array of size A plus an array of size A is going to equal another array of size A. Okay, so then we'll go ahead and initialize our data, right? So initialize our data, right? So I usually use just a little helper function for this. It cleans up the code a bit. And if I want to go ahead and change how I'm initializing my data, I don't have to go to some place in the main function, right? It'll just be a single call site that I need to change, right? Or a single, yeah, I just need to change the call site and then say some function, right? So we'll just call this init array, right? And we'll pass in two things, right? We'll pass in a pointer to the array and we'll pass in the size of the array. And then we'll say that this initializes an array of size in with random numbers between 0 and 100, right? Oop, spelled numbers wrong. Right. All right. So inside of here, it'll be fairly simple. All we'll do is a quick for loop, right? So int I is equal to 0, I is less than in, right? So in elements, I plus plus, right? So then I need to go ahead and include something now, right? So we'll include C standard lib, right? And this is where we'll get access to the rand function. Now, rand doesn't give you great random numbers, but it gives you decent ones. And if you don't really care about, you know, how actually random the numbers are, you're going to be fine, right? And we can also set a seed if we want to. It doesn't really matter here, so we won't. Right, so here we'll just do a of I is equal to rand, and then modulo 100, right? All right. Let's see. Let's see if we can make this fit on one line and stay within 72 characters, right? So initialize an array, size in with numbers between 0 and 100. Okay, that's fine. All right. So, right. So now we've got a function to initialize our arrays. Now we can just call init array, right? And we can call this on A and pass it in elements, and then we'll pass it to B as well. All right. So the next thing we'll do is we need to calculate our grid size, right? So how many threads are going to be in every single block, and how many blocks do we need to actually launch, right? So for this case, right, so we'll just, another comment, right? Initialize our CTA and grid dimensions. So in this case, right, so how many threads you want per block? For a problem like this, it really doesn't matter that much. Generally, you'll do something like 256 or 512 or 1024, right? In this case, we'll just use 256. Now, in other circumstances, depending on your problem, there'll be different numbers of threads that you might want, especially depending on if those if those threads need to cooperate with each other somehow, right? So if they're all going to access shared memory together, right? Shared memory is only accessible, or it's private per thread block, right? So if you have a problem where you have a lot of sharing going on between, you know, adjacent threads, you might have bigger thread blocks, right? In this case, we don't have any sharing going on, so it doesn't really matter. So in this case, right, we'll go ahead and just, you know, set int threads. This will be our threads per thread block is equal to 256, right? It's a nice even number. Then we have our grid, right? So our grid is a little bit more interesting, right? Or the number of blocks we want to launch. Now in this case, at least for the default case, it's pretty easy, right? So if we want to do 2 to the 20 elements, how many thread or blocks we need to launch? Well, that's just going to be in divided by threads, right? And because in is a power of 2 and 256 is a power of 2, right? Threads will divide into it evenly, right? Or I should say a power of 2 greater than or equal to the size of threads. But what if we don't have an even number of threads, right? So this is the more interesting scenario here. So in this case, right, we need to go ahead and do some padding, right? So our default cases, we'll just do in div threads, right? Now, if we want to do some padding, the way that most people do it is just with, we'll do in plus threads minus 1, right? And so we can look at this with a simple example, right? So what if we have 257? Our in is 257, right? So in that case, if we look at the division here, it's integer division. So 257 divided by 256 in the original case would give us 1, right? Because it would give us 1, remainder 1, right? But the remainder gets dropped off, right, with integer division, right? Because we're just storing, the quotient, not the remainder. So in this case, right, so if we do this quick, padding, right, plus threads minus 1, this ends up being 257, right, plus threads, so plus 256 minus 1. So it ends up being 257 plus 255, right, and this ends up being 512. So 512 divided by threads, right, that'll just, which is 256 in this case, is just going to be 2, right? And, you can look at other examples of this. If you want to do, say, what happens if you launch 255 threads, what happens if you launch some arbitrary number of threads, and you'll see that this ends up just working out and is a pretty concise way of padding your grid, right? So now we can, with our grid calculation done, right, we're making sure that, at the bare minimum, we're launching enough blocks, right? And now we've actually gotten to the point where we're going to actually call our kernel now, right? So here, I'll go ahead and just split the screen here. That way I can move back and forth pretty easily, right, between our kernel and between, our call site for our kernel, right? So we're launching vector add, right? And then when we're launching this, it uses the not terribly nice 3 less than, 3 greater than signs, right? And here we pass in first the number of thread blocks, right? So this will be blocks, right? And then the number of threads per block. And there's also 2 other parameters here that we could put as 0. So this is just going to be the amount of shared memory and the stream number, but we can just leave those as default because we don't care the stream, right? The default stream is fine. And we're not using shared memory, right? Because we don't actually have any reuse of values. So shared memory does nothing for us. So in this case, right, we'll just put the dimensions of our thread, of our problem, right? And then we have to pass in some arguments, right? So in this case, right, what are going to be our arguments, right? So that will go ahead and be A, B, C, right? So our 3 input arrays, and then also n, right? So n being the size of our arrays. So then we need to go ahead and change our function up here, our kernel up here, and we'll have it take our pointers now. So int A, int B, pointers, int pointer C, and then int n, right? So now everything's looking okay with our call to our function, right? It doesn't do anything yet, but we're at least calling our kernel, right? So now we can start actually writing our kernel though. So the first thing we need to do is go ahead and calculate our thread ID, right? So every thread needs to know who they are or where they are in the grid of threads we just launched. So, basically what happens when a kernel launch happens is every thread will be running the same program, and that program is just this kernel here. So if you don't calculate, your thread ID, none of the actual threads know who they are, and they're all just going to do the exact same thing, right? Which is generally not what you want. You generally want to have parallelism, right? You want them to be doing different things or accessing different pieces of data, right? So we can do calculate the global thread ID, right? And we generally put this as a TID, right? So thread ID. So int TID equals block IDX.x times block dim.x plus thread IDX.x, right? So what does this calculation give us, right? So we've got block IDX.x times block dim.x. This just calculates which block are we, right? So we've launched a number of blocks here, calculated down here. Now we need to figure out first for every thread, to which block does this thread belong? Okay. The next thing we need to do is we need to go ahead and calculate which thread we are in that block, which is what this plus thread ID x.x. You can consider this basically a base and offset calculation, right? So your base will be the start of a block, and then your offset is your thread ID x, or your offset within that block. Right, so now every thread knows who they are, right, in our global grid of threads. Now, the naive thing we could do, right, if we don't actually care about, if we're just going to have, every thread doing something, we would just do something like A of TID, or rather, C of TID is equal to A of TID plus B of TID, right? But this isn't exactly correct, right? It's correct in a lot of cases, right? Or at least in some cases, but not always. And the reason why is what happens if we don't launch a multiple of 256, right? So if we don't launch a multiple of 256, let's say we launch 255, well, technically 255 of these threads should be doing, they should be doing this addition here, but one of these threads shouldn't, right? Because we've launched, one too many threads. And this is just a, artifact of we have to launch even block sizes, right? So, what we'll do here is we can just do a quick conditional statement, right? So we can just do if TID is less than n, right? Right. And we can just shift this over, right? So this is just doing a check, and we can just call this, a range check. Right, so we just want to make sure that every thread, right, so in this case, every thread corresponds to a specific index in our array. And we want to make sure that every thread that we've launched, right, corresponds to a valid index. If it doesn't correspond to a valid index, basically it just kind of drops out of the program, right, or just gets masked off. And you can look more into my GPU architecture series if you want to know more about this idea of masking off threads. Okay. Right, so now we've got our range check and everything looks good here. That's actually it for the kernel itself. The kernel is pretty simple, and we're calling the kernel now. Right, call the kernel, but there is something that we need to take care of here. It's an easy thing to mess up, especially when you're first writing kernels and if you're using something like a unified memory. So kernel launches are actually asynchronous, right? And this just means that when we do a kernel launch, we will continue execution on the CPU immediately after the kernel launch. Not when the kernel is finished, but when the kernel is launched. So this means that if I didn't put anything else down here, my program could exit before the kernel actually finishes. So we need to make sure that that doesn't happen, right? And the easiest way to make sure that that doesn't happen is to just call something like CUda device synchronize, right? And this just makes sure that all the previous operations that have been sent to the device have completed before I continue on, right? And so now, technically my program is done, right? So I've completed vector add, or I've added the two vectors together. But it's always good whenever you're writing code, especially if it's your first time writing this code, is to add something called a functional check, right? Or something like a functional check to make sure that your code did what you expected it to do. And doing something like printf or cout and printing out a ton of things is not a very good way to do it, because especially if we're launching 2 to the 20 elements, right? Are you really going to go through and check to see if all 2 to the 20 elements are correct? Right. So this is where something like assert helps, right? So we'll include 2 more things, right? So we'll go ahead and include assert, right? And then we'll go ahead and include IOStream, right? And then for convenience, I'll just say using namespace standard, right? And I'm just using the namespace standard thing. That way I don't have to do, standard cout, etc. every single time. Okay. So here I can just do verify result here, right? So I've got a init array here, and then verify the vector add computation on the CPU, right? So this will run slower, but in this case, it doesn't actually run that, so it's still pretty quick. It's just additions. So I can go ahead and just do void verify solution, and what will I pass in? I'll just pass in the exact same thing as I passed to the vector add on the GPU, right? So int a, int b, int pointer c, and then int n. So I've got our 2 inputs and our 1 output, but our output now is actually filled with the answers, right? So here I'll just do a for loop, int I is equal to 0, I is less than n, I plus plus, right? So I want to go over all the variables. So kind of a neat thing to think about GPU programs in this case. Let's go ahead and get rid of the split screen, right? So one of the neat ways to think about GPU programs is that, there's this concept of loop unrolling where you take a loop and instead of, having a loop there, you basically just take all the individual computations and you just have them all, laid out in a big long line, right? So you can think of basically GPU computation, especially for something like vector addition. It's basically just going to be loop unrolling, but across threads, right? So, so let's go ahead and verify the solution. Easiest way to do that is just with an assert, and we can just check to see if a of I plus b of I is equal to c of I, right? So if they're equal, nothing will happen. If they're not equal, the program will crash, right? So there's our verify solution. So now that after our program's finished, we can go ahead and call verify or verify the solution, right? And then verify solution, and then we'll pass in A, B, C, and N, right? And then we can just print out here, program completed. And we can just say, correctly, right? And then a new line character afterwards, right? So now that's basically our program, right? So just run through it one more time. So we started out by just, setting our problem size and allocating some memory. Then we wrote a little helper function called init array up here. And then in init array, we just throw some random numbers into each of our input arrays, random integers between 0 and 100. Then after that, we select, kind of an arbitrary thread size, right? These are going to be a multiple of 32 generally, just because the underlying architecture, the warp size is 32, so that's very much encouraged. Then we set the number of blocks, and we made sure that we pad it, just in case we want to change our input size. Then we went ahead and wrote our vector addition kernel. In our vector addition kernel, we first had to calculate, our global thread ID. Then we had to do a range check just to make sure that if we're launching, something that's not an input size, that's not a multiple of 256, that we weren't illegally accessing some memory, right? So if we launch 255 threads, the 256th thread would be launching data that's out of bounds on these, right? And depending on your architecture, this could cause, something like a segmentation fault, right? So you don't want that. Okay, so then after that, we had to make sure we threw in a CUda device synchronize because kernel calls are asynchronous, and we're using unified memory. If we're not using unified memory, if we're just doing something like CUda malloc or CUda malloc and CUda memcopy, generally you don't see a CUda device synchronize in those codes because right after your kernel launch, you copied back the result explicitly. So you do a CUda memcopy from device to host, right? And that's synchronous, right? So that copy is synchronous, and so that implicitly synchronizes your program. But because we're using CUda malloc managed instead, that way we don't have to have two sets of pointers. We don't get that synchronization. And then we go ahead and verify our solution, right? So let's go ahead and quit out, and we can go ahead and compile this, right? So in VCC vector add -o vector add, right? No compiler warnings, that's good. And then we can actually run our program, right? And we see that it ran, completed successfully, right? So it did compute vector addition correctly. We can even profile it, right? Make sure that it's actually doing what we expect it to do, right? So we see that it did call vector addition, right? We have 3 CUda malloc managed because we allocated our 3 arrays, right? And then we see down here for a unified memory profiling, we see the amount of times it had to copy data from host to device and from device back to host, and then the amount of GPU page fault groups, right? So 24 here, and then total CPU page fault ended up being about 60. Doesn't really matter for us, right? This code really isn't about performance. It's just kind of a demo code. And then we can even trace this out if we wanted to. So we could do right. So we'll do nvprof and then --print -gpu-trace, right? And then we can get a trace of all of our events over time, right? So you see all the times we have unified memory copies where we have page faults, our actual kernel here, right? And when we're page faulting on the GPU itself, right? Here's our actual kernel. So we see our grid size and our block size. Okay. So what other things can we do, right? So it's always good to test a program with a couple different other conditions as well, right? So let's go ahead and open vector add back up. So vector add.cu, and let's just make sure that it handles non-power of 2 inputs, right? So we know that the CPU side will work fine, but does the GPU side work fine, right? So what if we do, 1 shifted over 20 times, plus 20, right? So now we've got a non-power of 2 input. Oops, got to remember operator precedence, right? It's trying to shift over 1 plus 40 times, all right? And then plus 20, right? So now this won't be a problem, right? So now we're doing 2 meg elements plus 20 elements, right? So now it's not going to evenly divide, and we can test that as well, right? So we can go ahead and do invcc, recompile this, test it again, completes correctly. We can make sure that it works on other input sizes as well. So does it work for, 1, right? We'll compile it, and it completes successfully, right? So the CPU program directly matched what the GPU program gave. Okay, so that's going to go ahead and do it for this episode, right? So we saw, step by step how we'd create something like vector add. And in later videos, we'll do things like matrix multiplication, cache tiled matrix multiplication, more complex programs, and then we'll also do CPU programs as well. But that's going to go ahead and do it for this time. As always, feel free to check out any of this code at github.com/coffeebeforearch. Right, so we've got, this is the CUda programming series where we've already gone over this before, right? So here's our vector add code, unified memory code. I actually think this code is quite, it's a bit more simple than this one, right? It's a bit more clean as well. This one went into prefetching a little bit. If you're interested in understanding a little bit about how prefetching works with things like CUda unified memory, go ahead and check that video out as well. But that's going to do it for today. I'm Nick, and I hope you have a nice day.